Lift off. Oh, and I forgot to take robot out of the intro, which is okay.
So you'll be part of like welcome to another episode of Labs Talk.
Yeah. Welcome, robots, too. Hi, robots.
Hello.
Robert Wille from TUM.
Robert.
Now you have to watch us actually just doing the intro. And I think this way it's actually nicer anyway, because when we take you out of the picture, we can see these ugly boom arms, which you really don't like. So that's why we can keep you. So
anyway, to get this started, this is our 5th episode in a series about quantum computing. And we did have a few guests already. Do you remember who we spoke to?
I'm not sure if I remember everybody, but we started with Isabel, right? Isabel was a really nice show because we talked about the basics of quantum computing, all the qubits, basically, entanglement, and that was really cool.
And that there is logic gates one can build in quantum computers, and that makes it a superset of.
We also talked to Nadim, right, about real use cases.
Not in that order, though.
Not in that order. Which was next?
We spoke to Anselme about post-quantum cryptography and how to mitigate that. Mm-hmm. So that was a use case, a real-world application, and something that will affect a lot of people.
And then the next real-world application, which didn't quite fit to quantum at this point, was then really with Nadim, right? So that was about the sourcing problem, where we could use quantum at some point, potentially, I believe. And then we talked to Isabel.
No, to Laure Lebars.
Laure Lebars. Sorry, Laure Lebars, of course. There's a heat wave going on. Right?
The president of the European Quantum
Quick Consortium.
Exactly.
Yeah, Quick. That's how it's called.
And today, Robert, you're our 5th guest in that series. And with that, now that we messed up the intro, I'll hand it over to you. This is an opportunity. Robert, introduce yourself.
Absolutely. Hello, everyone. Thanks for having me. I'm Robert. I'm Robert Wille. I'm here professor at the Technical University of Munich, and since the beginning of this year, also CEO and founder of a startup. By training, I'm a computer scientist, but I work in quantum computing for more than 15 years. I like to say I worked on quantum computing before it became cool, because when I started this whole thing, quantum computing in computer science was really a niche topic and didn't have the momentum it had these days. And as a computer scientist, of course, what we do, we develop software, and I guess that's what we want to talk about today.
Yeah. No, absolutely. One intro or one talking point we spoke about even just before. And when we spoke through the series, we had an episode that covered the physics of quantum computing. We spoke about qubits and entanglement and how to build those logic gates and everything. Very theoretical approach. And we had 2 other episodes that dealt with use cases. There is the cryptography part and how quantum computers will possibly break those algorithms for cryptography, and in particular that retail sourcing problem that Nadim explained to us, that seemed to be super complex and where a quantum computer could possibly solve a problem. But one thing we never really spoke about yet, even though Laure Lebars is head of this consortium, industry consortium, what we never spoke about is how does that physics get to work at some point. There's a lot of qubits all over the place, and there's a big, hairy problems that need solving. Robert, I understand you're working to fill that gap in between, right?
Exactly, yeah. I mean, as you said, on the one end of the spectrum, there is the physics and the quantum computers, the actual physically built machines. And on the other end of the spectrum are the end users, which hopefully can utilize those machines for their applications. And there's a huge gap, and software is supposed to fill that gap. That is kind of my mission. We've been building software or entire software stacks to connect end users who are experts not on quantum physics, but in the corresponding application domains. We connect them with the machines themselves. And if you think about that, that is very similar what we have with conventional IT as well, because also there we have computers built by electrical engineers, and we have end users not just from application domains, but actually my grandma uses his her mobile phone to, I don't send me messages. And by that, I have an end user who's definitely not an electrical engineer, can sending emails through a device which has been built by an electrical engineer. And now I don't think my grandma is going to use quantum computers soon, but end users, application experts should not have necessarily be quantum physicists in order to use these machines. And that's exactly why we need software. And that's what we're building.
Very cool.
Like a very random thought, like thinking about your mom and your grandmom. Like for every Christmas, a computer scientist goes home to fix his parents' problem. In the near future, do you see the quantum physicists go home and fix their parents' problem sometime soon?
It's a good question. I don't think so. My vision over the future of computing in general is we're going to work much more with interfaces, and maybe even in a world where not everyone has every particular computer technology back home. We already right now have all our computers and smartphones back home with their CPUs and GPUs. I don't think we're gonna have quantum computers back home, and this is actually just also more. They're not just CPUs, GPUs, quantum computers. There's actually neuromorphic computers, maybe DNA computers in the future. And at some point, maybe we're going to store all of them in some computing centers, and then we're just having interfaces access them. And then hopefully some smart guys on those computing centers can fix the problems, and we just have to deal with interfaces anymore. We're not there yet, and it's a little bit broader than just quantum computing, but I don't expect to fix my grandma's quantum computer at some point.
Things sometimes happen more quickly than you anticipate. When I went into computer science, computers were not very popular, and still fixing computers became the story of my life.
So, I mean, bringing us back to quantum physics a bit. I know we're going to talk about software, but the first topic we talked about was basically abstracting the hardware. I'm just wondering, is this already the right time to abstract the hardware? So there are different hardware platforms out there, right? We've heard from Google and IBM and 10 others probably. I think IQM, was it IQM? I don't know, something else, right? So all these hardware manufacturers who work on quantum, basically, how much are they different, basically? How diverse is that field? Is it like in the normal computing space, or like ARM and co, basically, or is it radically different?
Well, maybe something in between. I mean, those all the companies you just mentioned, they're building quantum computers based on a technology called superconducting, and which is one branch of technology, how you can do things. There's another one based on ion traps, another one on neutral atoms. I'm also not a real expert on that, but of course I have a rough understanding because I need to connect to those hardware providers and developers. And the bottom line is a little bit, there are different technologies out there which have different requirements. One is, I don't know, some of them need cryogenic temperatures, other work on room temperatures. They have different requirements of scalability with respect to qubits, different properties with how good they are with respect to error correcting. And because of those differences, of course, at the end of the day, the end user just wants to execute or run a particular application. And then, of course, it needs to be somehow translated to this particular technology, and within the technology, a particular architecture, things like that. So there are similarities also in conventional computing. We have different architectures. Yeah. Maybe the spectrum in quantum computing is a little bit broader because we also have different technologies in electrical engineering or in conventional computing, but the spectrum of the architecture, the physical possibilities are bigger in quantum computing.
Yeah, and the smallest common denominator is not the qubit, but there's more, right? Otherwise, abstracting doesn't make a lot of sense, right? So there's more commonalities among all these systems, I would say. Otherwise, it's gonna be.
It's the qubit. So like what I like a lot, particularly as a computer scientist, you have qubits. This is the main entity of the main physical entity of storing information in this quantum computing context. But then you have operations. How do you transform the state of one qubit to a following state? And wouldn't say this is all you can boil it down, and this is a very simplistic abstraction, but I like a lot of these abstractions, also the simplistic abstractions, because the whole thing, the actual technology is super duper complex. And if we want to make it work, as said, we need the software stack. And then because of that, we need to get computer scientists in there, and computer scientists love abstractions. We've got conventional technologies. You're going to see I'm using this reference quite a lot, but we have seen conventional computing becoming a success, not just because we had great electrical engineers, but we were able to abstract them that a computer scientist could run a program on a high-level programming language, or in the beginning, even on an assembly language, and just working with zeros and ones and not with current and with voltage and electrical resistances. And this abstraction is key to get eventually super complex software and applications running. And this does not mean we should ignore and neglect physical properties, but it makes sense to build up a stack where you're very physical and try to consider physical requirements at the lower levels. And through the stack, you abstract more and more so that the end user can focus on his or her program or goal or objective, and not have to become a quantum physicist.
Going back to the question whether it's the right time to build that abstraction already, all of this sounds like there's a lot of choice already. And when we spoke to you for our pre-chat the other week, we virtually met you in a quantum computing fair here in Munich. So to me, this looks like not only the market exists, but the market has to offer quite a variety of technologies, very fundamental, very basic technologies at this point to stay with what I understand. But that I feel like there is this need to abstract the hardware away already. And I guess that's where you are and where you're trying to build this common interface to access different vendors' quantum hardware. Is that assumption right? And with that, what are the common expectations from the work that you're doing, from the market and from research?
Absolutely. I mean, the field is really leaving the labs. So this is really not a basic research topic anymore. And you can really see that. I mean, you need computer scientists or the stack if things get too complex. A couple of years back, 10, 20 years back, we had first quantum computers. They were composed of 5 qubits, and you could run your application. So your toy example of that, you can do all that manually. And at some point, you reach a point when you have hundreds, dozens, hundreds, thousands, at some point, millions of qubits, you cannot handle that anymore. I like to compare that with a puzzle game. Puzzle game of 5 qubits, it's a infant's game, right? A puzzle of 100 will still be easy. If you have a puzzle of 5,000 pieces, you're going to take a couple of hours to fix that. We have the very same thing for quantum computing as well. And that's what you see in the fair you referred to. It was actually the World of Quantum here in Munich last week. It was a nice showcase of how much the community evolved. It is still a hot research topic, but now industrial players are there, industrial players who build hardware, industrial players who develop software. Our own company, please excuse the shameless plug, our own company was there as well.
Okay.
And also, and that's the important part, also end users were there. So now, I don't want to mention explicit company names, but the who's who in the IT industry is there and tries to commercialize and to create products. So it is really a development from research to the industry, to the production ready levels, and to applications.
Also coming back to the pre-chat, I think we talked a bit about programming languages, right? Some years ago we had assembler, and then we had like higher level programming languages, and it might not be quite fitting, but at some point we got these low-code, no-code programming languages, environments where you could just basically stick together your program. And now you know it, right? That the recent trend, large language models and agentic AI, now we just wipe code everything and
we just
get it done, basically,
beyond
right?
The low code, it's literally no code. It's wipe coding these days.
I'm just wondering, for quantum computing, right? And I think you also know Qiskit pretty well, which is this SDK for quantum computing from IBM, I believe. Where are we basically, right? So are we basically on assembler level, or are we close to building visual tools, or are we able to train AIs already that do the work for us? So I'm just wondering, where do you see us right now?
So roughly, I mean, of course, the comparison is not perfect, but we are more or less on an assembly level, and we have super duper nice visualizations of this assembly level as well. But again, on the lower level, so we are there yet. And of course, there are also high-level programming languages being tried out and researched. Again, you can compare that very nicely. The development was similar, I don't know, a couple of decades back for conventional computing. You started at some point recognizing electrical engineer cannot master that anymore. So we needed some abstraction. The first abstraction was assembly, and then you had programming languages, and then indeed it evolved to this low-code, no-code thingy. And we're there very similar with quantum computing right now, which makes kind of sense, but I also try to work a lot that we are not trying to reinvent everything from scratch again, that we not now take another 50, 60 years or so to develop the same software stack. So that we try to copycat, to learn from past experiences as much as possible. So we don't have to start from scratch, but we can also not just take what we've got. We cannot just take a conventional programming language and then just use it for quantum computing. There needs to be adaptation, and this is something which is being developed. We're leaving at the moment the assembly level. There are lots of discussions, MLIR, QAR, about our higher levels, about integrating that to conventional languages. Also very important, integrating that into some sort of HPC systems, because this is eventually a huge use case where you're going to use these computers. And right now, it is not as sophisticated as we have that for conventional IT, but we're getting there, and hopefully we don't need the decades we needed to develop it from the first time.
Very cool. I'd have one more question actually, and that's just so I mentioned Qiskit quickly, right? And there are probably other SDKs out there to program quantum computers, but how do you translate the problem that you might have, an optimization problem, into the program actually? So is that something, I guess right now I couldn't ask an LLM about that because there are no examples or little examples out there that probably work, right? So LLMs wouldn't really help me. So I need to have some quite in-depth knowledge basically about how to program a quantum computer probably, and what are the steps that you can basically tell us about to translate this problem statement into a program. Maybe also how do you evaluate first if it's applicable at all, for example?
Right. This is exactly the case right now. A lot the best end users for quantum machines today are physicists, which might not in the long run be the target group, because right now you need a lot of quantum computing expertise in order to use the machines. I'm still a little bit optimistic. First of all, it depends a lot on the application. We have several classes of applications where you roughly have some sort of like a quantum algorithm which you can just take, and then you just have the quantum algorithm then consists of several steps. Some of them are very quantum computing, not really quantum physics, but quantum computing heavy. But there's one part, an oracle, for example, in which you kind of have to encode your problem instance into it. And the rest can be used a little bit like boilerplate. This is a very sort of like naive way of looking at things. If I really have no clue about quantum computing at all, you could just take you have an application. Maybe you can check out, okay, in what class of quantum algorithm is suitable for this application. Then you take this algorithm as some sort of a black box, and then there's one component which you now have to, in which you have to encode your problem instance. And this encoding is to some extent similar to just encoding my real-world problem for a conventional computer. And for that, again, software, we could develop software so that you can do this in a push-button fashion. For some classes, this is one approach how I could see that. And then for these kind of problems, it is, in the best case, the end user doesn't have to care about how to do this. I have some solutions to. I'm throwing my problem instance into some sort of black box, and then the black box does the encoding and then applies the algorithms. They are also to really utilize quantum computing at best. It might also be there might also be some applications where you want to explicitly exploit quantum computing properties, and then you might have to deeper into that. But also here, this is harder, but also here in the long run, we computer scientists, we tool developers, it's our task to make it as easy as possible, as push button as possible, and maybe in the future as low code, no code as possible. I'm not saying that this is what we're working on right now, but in the long term, I would love to just tell a machine, okay, can you please solve this, and then this machine does all these translation steps. But for that, we need the software stack first, and right now we're sort of between assembly and high-level languages and these encoding things. But to be honest, it's no rocket science, and then go back to abstraction. Once we understand how we can abstract all those quantum computing, excuse the term, atrocities, which non-quantum physicists don't understand. Once we can abstract that, then we can build up this stack step by step, and that's what we should do, and that's what we're doing.
building that software stack. Like, I'm a computer scientist by education as well. I started in a different century with all of that, and I've observed the entire development of software architectures for quite a while. I feel along the route for the past, I don't know, 80 years since computing was invented, the entire discipline and the entire industry has made so many mistakes. Now, at this point of research and development, building that new stack that you're working on, is that a good time, a good point in time, a good opportunity to avoid some of the mistakes, to do better this time, to start over with a new architecture and a new technology?
I definitely, I think so. I mean, that's why I said we should not reinvent the wheel. We should learn from decades of experiences. This is actually what my goal is, not developing something new. My goal is understanding what is needed and then checking what did computer science or engineering developed over the past decades, take that and then adjust it so that I can use it for my current problem. And in this regard, I'm a big fan of reuse. I'm a big fan. I honestly believe that you have a community here with some problems, you have a community there with some expertise and potential solutions, and you have to bring these communities together. And this is exactly what we're doing our work, and getting then so like also inspirations how we could maybe change architectures, even conventional architectures. This is also part of the game. It's not that we are completely changing everything, but there's a term quantum inspired computation. So indeed, something we learned from quantum computing is now actually being applied in conventional computing as well. Because you got some interesting ideas and you learned something from this one field, which you can apply in conventional computing as well. And this gives you a benefit. So these kind of things happens, and we're doing this as well.
Very cool.
Sounds very promising. There's a lot of things coming, I guess. Now, after I believe we asked most of the questions, we typically arrange our show in a way that we end on a forward-looking note. With all the work that you're doing, Robert, let's talk about the near future a little bit. We started this episode. I was thinking about repairing my quantum printer for my parents at some point, and you already
repairing your quantum printer.
That's the typical computer science.
Your quantum fax machine.
A quantum fax machine.
You're cryptographically safe.
I'm crypto safe. Yeah, that's true. I'll never have to repair a quantum printer for my parents. Nevertheless, you already ruled that out. I won't solve that for my parents during Christmas time. That won't happen. But still, there is the industry exists. The work you're doing is real, and everything is moving forward at a very fast pace. Like now, when we do this series on quantum computing, this is because it's something super alien to us. But when do you anticipate this to take up and make it into the broader, say, appearance? And when will people really get in touch with the technology one way or another? What happens the next 5 years?
Yep, this when question is always a little bit. I try to usually dodge them because when I say something like in 5 years we're gonna have this, someone digs up this podcast and I look like an idiot because things always turn out differently than we anticipate. But what I really see is that indeed quantum computing does make it into practice. There's still a couple of challenges. I'm not saying we have this already right now, and there's actually, to really be honest, there's a huge discussion about what are going to be the business cases and when do they come. It's of course a huge thing because also people who are investing in the technology, they're asking for their return on invest. And the honest answer is we cannot make any promises here. The question you have to ask yourself a little bit, can you afford not getting involved right now? Because then if indeed in 5 years there is the breakthrough and you haven't invested in the technology yet, you're gonna have a huge time catching up, because it's not that you just can sit it out, wait until the technology is there, and then you can become an quantum expert. And also with respect to sovereignty, both with respect to different world regions, but also with respect to other industry, you should think about that. What I believe I don't think it's going to be this end user like my grandma thing. Like I might be wrong about that. I think about this technology is going to be part of computing centers, HPC centers, where they have high performance computing machines, CPUs, GPUs, or now the QPU. And then maybe in a perfect world, the end user doesn't even care with what technology his or her problem is solved. He just submits the problem, and then the HPC center and the infrastructure, the stacks, take care of how to decompose the problem and what technology to use. And that could be that is sort of like the vision or what I expect how we're going to use these technologies, because it's not an daily, everyday use. It's not a mobile phone or a smartwatch. It is more like an HPC accelerator, which we're going to use. So I see this is more the end case. So eventually, probably domain experts are going to use this machine, not my grandma.
I would have maybe another final question, actually. I mean, most companies out there probably deal with software, right? So that's why you're absolutely right in the software stack, basically, right? Not everybody creates their own quantum computer, basically reinvents the wheel and so on, basically. But what would you recommend for companies like SAP, other big IT companies, for example, to actually to get in touch with quantum computing and to not miss that train, actually? Because right now we're super dominated by AI, large language models, of course. Of course, first of all, it's an investment decision that we also do something on the side of that. Of course, that's a decision. But what are the tools, the things someone should get involved with actually and get an understanding of?
Absolutely. So like it is indeed getting involved, kind of literally, not literally, but so like learning to spell quantum. So getting a little bit how the basic concepts work, not necessarily becoming a quantum physicist, but having a rough understanding about the idea of quantum computing on an abstract, intuitive level, and then sort of like getting involved. The best case, trying a toy example, which doesn't bring you any commercial value, but getting a toy example to just experience how would the flow look like. And then most importantly, I think, because the toy example have one big problem. There's a cool use case. Like, I don't know, there was one company which wanted to improve the entire supply chain of their company. A huge problem. With today's machines, you cannot do that. What you can do is you can solve a travel salesperson problem with 5 cities. So this is the toy example. So this, of course, is always a little bit underwhelming. So if you want to invest, or if I want to convince my boss, you have to invest in quantum, and all I can deliver to you until the holidays is we solved travel salesperson problem with 5 cities. It's not going to convince. But what you can do is you can do research estimation. You can explore, is this application actually suited for quantum computing or not? And this is something you cannot, you don't need years for that. But you cannot also just sit it out and then overnight it will come to you. You have to explore that. And I think toy examples and using research estimation, exploring, is this an application which can be solved for quantum computing or not, so that you get an understanding as a company, for example, I have these kind of problems, and those problems definitely couldn't be solved better with quantum computers, but these problems have the potential, and because of that, I need to dig in now to understand whether or not I can utilize this potential, and then maybe I figure out I cannot utilize after a couple of months or so. I figure out I cannot utilize for that, but maybe for that. But then I need a 5 fantastic trillion qubit computer for that, and then I may have to start. Okay, maybe I should do the encoding better. Maybe I should, like we developed over decades, high-end software for solutions. If I would travel back in time and would give, I don't know, a company in the 1990s and state-of-the-art computer today, they wouldn't be able to utilize the potential because the software wouldn't be there either. So that's what I meant. It is not enough to just sit it out and wait until the hardware is there, because then you have the hardware and you have no means to exploit the hardware as best as possible. And this development can and should start already right now, even if the machines are not that scalable. And with estimation, can work to that. A best case scenario to me is you identify the application, then you implement the toy example to get a first try, then you implement the real use case solution and estimate what would be needed. And if you then get up, I need 5 fantastic trillion qubits, you optimize your entire software stack until you're down to 1 million qubits, and then you might be in a range to what could be there in a couple of years. this doesn't, hope it makes sense. This doesn't happen overnight. This is something you have to start now so that you're ready once these machines are there. That would be my advice.
Perfect.
So just to make another stupid joke, I guess we can end on that note, and to paraphrase Bill Gates, who once said 640 kilobytes should be enough for everyone. I guess we can conclude 640 qubits are not enough for everyone.
Yes.
Excellent.
That's probably something safe to predict.
Yeah,
Absolutely.
I'm going to have 640 qubits in my smartphone soon. Right?
Awesome.
Whatever.
Robert, thank you so much for your insights. Amazing. Thank you for
Thank you.
spending your time
Thanks for
with us.
joining us.
Thank you very much.
Bye-bye.
That was
Thank
fun.
everybody for
Ciao.
watching.
Bye bye.